Okay, so I've been working on operating systems. Pretty much you name it, I might have worked on it. But the very last operating system that I worked on was the kernel for the Wii U, which we wrote from scratch for Nintendo, or at Nintendo in Redmond, Washington. And we actually wrote two kernels because we couldn't make up our minds. So we did two instead of one, but from the ground up. I'm now working at Google on the Android Linux kernel, the team that does Android work on Linux, not device specific, just for any Android device out there. Prior to that, I worked on what became Windows 2000, worked on AIX and things related to Solaris, file systems, distributed file systems at Veritas, and most recently at a startup for 2.5 years. Well, there was a Sanifest effort at Veritas that I was involved in, also the Veritas file system, NGFS, and a few others. Yeah. So anyhow, I've been building operating system stuff for the last 30 plus years, and all of them have been written in C. There were two that were actually written in C++. The Nintendo Switch kernel written from scratch, that's written in C++. And there was kind of a not too successful or not too well-known microkernel called the Chorus microkernel that had been written in C++, but pretty much all of them are written in either C or C++. Of course, if you go to the mainframe or some legacy environments, they won't be written in either C or C++. But pretty much everything that is mainstream, ignoring the mainframe and ignoring the I series, which are the only surviving platforms that are not C-based, they're all written in C. Of course, C and C++, they're unsafe languages, meaning if you have a bug and you access if you have a bug, this can lead to invalid memory references, and these invalid memory references can be exploited by a hacker, and your piece of C code or C++ code can be taken over and exploited. Malicious things can happen afterwards. Now, the whole of the world infrastructure is sitting on all of these kernels written in C. You name it, it's a kernel written in C. Mac OS, Windows, Linux underneath Chrome OS, under Android, Linux on servers, AIX, Solaris, HP, UX, they're all written in C. And C is unsafe. Well, C++ is also unsafe. Yeah, iSeries is a beautiful thing. Yeah, no, that's a whole talk on itself. It's a beautiful single level address space with capabilities. You cannot forge the pointers, and it's a thing of beauty. The database and everything is single level address space, etc. Yeah. So just as a historical side note, IBM put $1 billion+ into future systems after the systems 360, and the future systems was going to be the thing after the mainframe. So future systems was too big, and it kind of died. And from there came system 36, 38, AS400, and iSeries. But it's a thing of beauty. Whoever wants to look at hardware protection and capability-based system that ever shipped that actually works, iSeries. But let's leave it at that. There were many failed capability-based systems in hardware, and let's not get distracted on that. So anyhow, so we have C, and we have a mountain of C code that is unsafe. And what we have here is a new language called COOGL, C Concurrent Object-Oriented Generic Language, and that's what this presentation is about. By the way, there's a sister presentation being given on the 12th in Sunnyvale in the same C++ users group. I think in Synopsis next Wednesday, about compare and contrast between COOGL and C++, more about language design. This one is meant to be more about what is it that makes this language safe, and what can we do with this language? What should we do with this language? So anyhow, that's me, and that's the URL for this. There's a book in there, and of course, the compiler is meant to be open source, and the book is meant to be free for download. I'm kind of reserving the rights if I get it printed in hard copy to help fund the compiler some more, but you can download it and do whatever you want with a PDF of the book, and it's the language design is done, modulo, textual corrections, and maybe some technical deficiency that maybe you guys will help find if you put some effort into this. So why do this? Well, of course, the world's infrastructure is all written in C, and it's unsafe, and all of our stuff is at risk. Malicious entities, government agencies, the NSA, the spy agencies of all of these countries can subvert these systems by exploiting bugs, and any of these bugs expressed in either C or C++ code that do invalid memory references potentially can become a way to take over your system. Now, if we wanted to re-engineer a huge code base, like a whole kernel, into a safe language, well, you can't do that immediately, trivially. You have to do it incrementally, step by step. It's a huge investment. But to be able to do that, you need a language that is incredibly close to C. So I'm going to ignore C++. C++ has all of the problems that C has, and a few more related to object slicing and a bunch of other things that I'm not going to get into. But so let's just talk about C. So if we wanted to rewrite a kernel from scratch and throw away all of the code and not reuse any of the code, maybe we could use Rust. But then you're throwing away all of the code. It's hard to do it incrementally. And if you wanted to use any of the other safe languages like Java or C# or Eiffel or Go, they're all garbage collected and they don't lend themselves well to re-engineering a kernel. A kernel is a thing that sits there giving you services, and it's has entities that are actively being used, a file that is open, a network endpoint that has been, connected to something, processes threads. And when these things are not being used, say the pages of a file where the data of the file are being cached, or the inodes that are being kept in memory, or the directory name lookup cache entries, when these things are not actively being used, they want to be preserved in memory because you might have just finished closing a file, you just read it, now you're going to open it again, and you're going to want to find the name in the directory name lookup cache, and the inode in the inode cache, and the pages in the page cache. So the things are very fast. So you can say the kernels are really caching a lot of stuff, and to put all of that caching under the control of a programming language and a garbage collector is not a good design choice, particularly if the kernel has already been written and you want to re-engineer it to make it safe. So COOGL is a language to re-engineer these systems and make them safe. Happily, I ended up at Google. I started there 5.5 weeks ago, and I have a subversive plan to begin to re-engineer something in specifically the Linux kernel into this language. Of course, Google itself uses Linux everywhere on servers. It uses it under Android, uses it under the Chromebook, and etc. But it'll become my 20% project. There's a lot of people at Google that contribute to the Linux kernel, so there's a critical mass. It might be one of the few places where this could get done. It's not officially a Google project, but they have this really open attitude towards open source. Yeah. So anyhow, other reasons why I have this language, well, because C needed to evolve, and C++ is too complex. So none of those C code bases ever got re-engineered into C++. So the two languages live on with huge code bases, and if they wanted to re-engineer a kernel into C++, I would still not make it safe. It'd just be, you just change the language. And in any case, as an industry, we must do something about it. It's been many, many years since there was a divergence in the industry. There used to be safe languages like Algol and Ada and others that would not do invalid memory references. Ada could do them, but there was this huge effort to make things safe. And sadly, all of these things are roadkill, more or less, though Ada kind of survives still in some defense systems. And we ended up all in an unsafe world. But all of these kernels need to be made safe, otherwise the whole infrastructure of the world is at risk. So what is it? Well, it's a simple language, very close to C. I'm going to show you a lot of stuff. I don't mind questions, but I might push the answers till later because we might get to the answers to your questions. So I might just answer them or push them out. Okay, so the goal of the language is that it be simple and it be small and it be as close as possible to C, but it be safe. That it doesn't have undefined behavior, which is a big problem that is getting worse with C and C++. Well, because we're evolving the language, I wanted it to be object-oriented and to have generic programming and to also have a notion of modules. Now, it's an open source compiler. The compiler is not finished being written. It's halfway written. And there's a book that is completely written that is free to download. Now, the second line here says it's compiled into readable C code. When you write a new compiler, you can marry it to a compiler family. You can marry it to the GCC family and use their code generators. You can marry it to the Clang compilers and use their code generators. And the reality is that all of these kernels sit on top of C compilers from these vendors, you know, the IXC compiler or the HPUX or the Solaris one or the Windows C compiler or GCC or Clang being used depending on what flavor you're who you are using Linux. So you want to be able to use the underlying C compiler that compiles those kernels because you're going to want to evolve those kernels little by little. And you want to use the underlying C compiler. The underlying C compilers quite often have special ABI things and intrinsics and other things that get used only in the kernel, and you have to be compatible with that. So forcing the language into a marriage with a specific compiler family tree, it would be the wrong choice.
So are you taking questions in line or at the end?
Yeah, I just said that. You can ask and I can defer or I can answer.
So if I understand correctly, this is a COOGL to C compiler.
Yeah, it's a COOGL to C compiler, yes.
That means it cannot be any safer than the underlying last mile C compiler.
Well, that would be true. Yeah, that would be true. Sorry that I'm interrupting. That would be true, but then you couldn't say there exists any C compiler because any language that is safe because at the end they all get expressed in assembly. Assembly is not safe. C is not safe. Is the code that you generate. You can generate safe code. You can generate safe assembly code. A safe language can generate safe assembly code because it's designed to generate the right code. So the fact that we're compiling into C doesn't make the language less safe. Yeah, so there's been two compilers, there's probably many more, that were generating C code originally. So the original C++ compiler compiled into C. The Eiffel programming language, as most people don't know about, it's a great language, very pretty. Eiffel also compiles into C. When you look at the output of these compilers, the C that they produce is not readable. It's not meant to be consumed by you or me. It's meant to be consumed by a compiler. So it's as if they generated this kind of inscrutable stuff. Now, the goal here is to produce code in C that is readable, down to the level that I'm going to preserve the indentation. I'm going to preserve your comments and variable names, function names. There might be a bit of mangling. The idea is to gain trust in the compiler. You can diff your original code, your COOGL code and the generated C code and see, oh, okay, it's all the same. Oh, here it added a constructor, here's some virtual dispatch, here's some destructor or copy constructor or something that it did to return tuples or something. But to make it easy to gain trust in a compiler, it's generating readable C code.
How can you stop maliciously modifying?
Well, there's no way to stop. Yeah. Yeah. So because this is tools based, there's nothing intrinsic in code signing and lineage. Well, imagine if the compiler was signed and every step of the build process was signed and all the compilers were trusted. It could be done, but at this level, it's not a goal. Yeah, so that's more tools to be built on top, but it's not a goal of the language itself. But yeah, it's an important question. Do you trust your compiler? Is your compiler putting bugs in your code? Is your compiler putting backdoors? Sure. Yeah. So we all should know Ken Thompson, the father of Unix and the father of B, which is the father of C. Ken Thompson and Dennis Ritchie did Unix, but Ken Thompson was kind of the lead guy. His Turing Award pitch is about trusting trust, and can you trust a compiler that somebody gave you? It can put backdoors into the generated code. He has a nice paper, and of course he refers to those ideas from before his time. There were other people's ideas, but yeah, there's a question of trust when you're compiling and generating code, all the way down to the hardware. Is there hardware compilers putting backdoors into hardware? Right, that's an interesting question too. So now more about what is it. There's a common subset between C and COOGL, and I call this subset a C lean, and it's really exactly C minus the preprocessor, minus prototypes, and minus old-fashioned KNR C-style function declarations. That's the one that came from ALGOL. All of the declarations in C and C++ now are written as in ANSI C, but the old style declaration is gone. And this subset of C, also, when you're going to write a cast, you use a keyword cast in parentheses, and that replaces the nameless, keywordless cast. Now, some other minor idiosyncrasies are gone. But this subset language is context-free. It means you can parse the language. You can parse any program without the aid of a symbol table. This is important for tools, syntax highlighting tools, etc., where to actually do anything, you don't have to consult what a construct is. So C is not context-free. C++ is definitely not context-free, but this subset of C is context-free. From this subset of C, which is code that you write in this C lean, can be moved between C and COOGL easily. Of course, you have to do something about prototypes when you compile it as C, and you might need to include things when you're compiling it as C, and you may have to do something with your cast. But the idea is to have a subset and evolve a subset. This is, let's not preserve all of C. Let's throw away a few things. And the preprocessor, go ahead. Excuse me?
Are you going to go through the benefits of these?
Of these specific things? Well, there's a whole chapter about what are the differences between the two languages in the book, and it's very detailed. And particularly if we were to go drill down, well, if you remove the preprocessor, what do I do for X, Y, and C, and etc. All of those are described there. So I'm not going to go through those now, but we can talk offline, or you can read it in the book.
The idea seems to be get rid of things that you use unsafely.
Well,
Easily unsafely.
not necessarily. This was just a bit of house cleaning to start with a slightly cleaner language. Like, well, what's the benefit of removing the old K and RC style function declarations? Because you can turn them all into ANSI, so why have that? Just simplify the language a bit. Casts, it's always nice to be able to grep a code base for casts, and just to grep, to search for casts, you have to actually parse to know when you're using parentheses. Because yeah, so that's that specific one helps actually with making it context free, and I can go into that. Well, just to answer,
Talking about to have a symbol table that decides it's a function.
so well, you do have to have a symbol table, but not to parse.
I meant to parse.
Not to parse. You have to have a symbol table so you can do all the type analysis and generate the correct code. But to actually parse, when you go parse this in C, you don't know what it is. Is it a cast of the expression B into the type A, or is it call the function A with argument B? And it could be, you could go three ways. And what is it? An expression casted to a cast, or is it call the function A with argument B, and it returns a function pointer, which I call with argument C, and that gets parsed completely different. And you don't know how to parse it unless you look these things up in symbol tables. But yeah, I know. But anyhow, it's just making the language simpler. So, so the idea of having this subset is that if you're going to really re-engineer a huge code base, you're going to have to do it step by step. And the idea is to have something that you can compile both as a COOGL and as C code. Of course, if you're compiling it as C code, you're going to need to include that into a C file that has prototypes, maybe has other pound includes, and you'll need things like this pound define if a cast with a type is just a type, just so that it compiles under C. So just a bit of Scotch tape, and then you can still build as C. So say, for example, you wanted to have this little ambitious project of re-engineer a kernel, let's say Linux. How do you do that incrementally? Well, you're not going to do it all at once. You're going to do it step by step. So you could start with, well, the whole thing is 100%. Let's just talk the kernel, not kernel modules, not device drivers, not file systems, not other kernel components, but the kernel per se. So the whole thing is 100% C now, plus some assembly. Well, you could maybe make some effort, and now you have 1% of it is in this C lean subset. When it is in this C lean subset, you can still build the whole kernel with a native C compiler. Make sure it works. You're still not introducing the new compiler. Maybe you can do a bit of more work and you're still building it with just a native C compiler. You're not switching the compiler yet. At some point you can say, okay, those 1 or 5%, however much I've achieved, I'm going to begin to compile those under the COOGL compiler. Now, the COOGL compiler is generating C, is using the same native compiler under you. So it's all calling convention, all compatible with everything else that's being compiled as C. Of course, if you only re-engineer 5% of your code, the kernel is not going to be safe. And you have all of the device drivers and file systems, none of it is going to be safe. For example, when Mozilla Foundation, they re-engineered some part of the browser, and they did that, re-engineered part of the browser in Rust, but 95% of the rest of the browser is still in C++. So, well, the browser is safer in that area where it uses Rust, but in all of the other areas, it's still exploitable. Okay, so the idea is to little by little begin to re-engineer this thing, be able to compile it both ways, and at some point you're throwing the switch on this growing percentage, and at some point you get to the spot where you have maybe the whole kernel is in COOGL, and at that point you begin to work on the file systems. Well, let's work on one file system, and you repeat the process for that file system. Let's work on some networking, or let's work on some device drivers, and little by little you put a lot of effort, and one day you're done. Now, a bit about the design principles of the language. Keep it as simple as possible. Keep it as close as possible to C. Learn from the ancestors. The ancestors of this language are Simula 67, from where all of the object-oriented stuff came from. Of course, people were doing object-oriented things in other languages even before Simula 67, because, having a series of branch tables and function pointers or things that you can go to that are kind of type dependent. That style of programming is even before Simula. Yeah, CLU is a research language that Barbara Liskov did. And it's basically the first language that have generic arguments. And even when she did CLU, I think it was MIT, I'm not sure, Carnegie Mellon, the type arguments, what you could call like the template arguments, even then you could specify the requirements. You could say, well, you can specify this type as long as it has these requirements, and it has these methods on them or these operations on them. So even in those days, this is all before templates in C++, Strustrup could have read the paper and maybe tried to do templates better. Anyhow, the goal of the language is to be done. I'm not a languages guy. I don't want the language to be self-ballooning. It's complex, so we need more complexity to fix the complexity. Just keep getting it bigger and bigger and bigger. So the idea is not that. The idea is to get it done, use it, and be done. And don't evolve it more, polish it a bit. Kind of like what happened with C. C wasn't written by language guys. It was written by Dennis Ritchie based on B, and well, B was based on BCPL, and they wrote C so they could rewrite Unix from assembly into C. That was their goal. And as soon enough, C was good enough for that, then they kind of stopped adding things to C, because why add more? At some point they added typedef, and at some point they added a few other things, and the preprocessor came even a bit later. You can tell it's a total wart, right? The preprocessor. And C stayed sane for a very long time. So the idea is not to create a cottage industry of books and conferences and stuff to tame the complexity of the language. It's the opposite. So I already said that I want to use the underlying C compilers. I don't want to marry it by force into shotgun marriage into one or the other competing open source compilers. Gain trust from the C programmers. I can diff their source code and see, how things got produced. Well, and I already said all of this. The generated code is going to preserve everything that you wrote.
So, since you're aiming to preserve source code structure, that rules out some types of things, or actually simply, such as eliminating heavy recursion.
So,
eliminating heavy recursion is not that simple.
But that's what the C compiler is for. Yeah. So the question is, because I'm trying to preserve structure as much as possible, I'm missing opportunities to optimize. And my goal is not to optimize things at this level, because there's really good C compilers. They're going to compile that C code. They'll deal with the tail recursion. They'll do all of the things that they need to do a great job. So this is tools oriented. I'm going to take this language, I'm going to compile it into C, and then I'm going to let all of these great C compilers do all of that great stuff. Of course, when I say preserve your names or variable names, there's some amount of name mangling. But this is an example of how simplicity breeds simplicity. So Well, there is no function name overloading, meaning if you have a function, when you call it, it is that function that you're calling. There's not a plethora of functions out there. Same as C, exactly. In C++, when you call a function and you pass the wrong number of arguments, you're not told, hey, you pass the wrong number of arguments. You're told, I can't find a function that matches that. It's like, no, I just passed the wrong number of arguments. It's just looking for some other overload with more arguments or something. So if we don't have a function name overloading, it means that at some point you have to mangle names. So say you have a class stack and has a member function push. Well, push is declared within the concept of the stack class. When it gets compiled into C, it cannot be called push. So the mangling is literally stack underscore push. Why? Because, well, I specifically hate leading and trailing underscores. So leading and trailing underscores are not allowed, and double underscores are not allowed in the identifiers. What does that do? It simplifies the language. The mangling is so simple, I just explained it. There's some other little aspects with private and protected, but the bulk of the mangling is that you can understand it is specified in the language. It's easy to understand. Now, a lot of the reasons why you have these underscores and underscore uppercase letters and double underscores in C and C++, that's so that you don't pollute the namespace, because of pound defines kind of are like you're throwing paint in all of these codes. They go and replace things willy-nilly, crazily. So because we don't have a preprocessor, we don't have pound defines, then we don't have to worry about having a place where we can do all of our library underscore uppercase letter things in a dedicated namespace.
One of the ways of safety is to have variables that don't change. And so SSA might be a way in which you could possibly do
Yeah.
and
Yeah, so that's too far away from C, but there's some aspect of that when we talk about array descriptors. So I'll get to that in a moment. Okay, so what makes it safe? This is really the bulk of the presentation. I'm going to be switching between a variety of documents. What is the goal? The goal is to prevent invalid memory accesses. Of course, we haven't defined what an invalid memory access is, but we're going to get to that. Also, we want to preserve C's ability to carefully lay out data structures in memory. Why? Because this is where C shines. I think in my theory of why this language C succeeded and all of these other languages failed is because in C you can very naturally have a piece of memory and you can lay out a header and maybe another optional header after it, and maybe some variable length data, and maybe some trailer, and maybe an optional trailer that you don't put, and then a footer, and you created a network packet. And you lay that out so beautifully. You just do cast, and you increment by the size of structures, and you just lay it out. And this is a network packet, and off it goes. So to lay out memory carefully in C is beautiful. You try to write, a TCP/IP stack in Java, but you're going to do an array of integers and form the payloads with arrays of integers. I mean, how do you do it, right? If you cannot just arbitrarily point at memory and do casts. So we really want to preserve that. Otherwise, you couldn't preserve these huge code bases. Now, something that's an important insight is that, well, there were other insights. I didn't list them all here. That when you externalize memory, when you take a chunk of memory outside of the program that is running, and you put it on disk because it's metadata for a file system, or it's metadata for a database, or you put it on the network, or you put it maybe on some shared memory. When you do that, you never put pointers in there unless you're a confused programmer. Yeah. Yeah, so in general, you don't put pointers there because the pointers are going to be meaningless in the other machine, or they're going to be meaningless to the address space of another process, or, over the network or on disk. You cannot trust them. So, at worst case, you might put offsets within the memory area or something, but you would never put pointers.
The standard model is when you're serializing something, you replace all the pointers by offsets.
Yeah, exactly. Yeah. So when you're serializing things, you do that, or if the data is going to live in process and out of process often, then you might just do all the work with offsets or something. But it's an important insight because when you're actually laying out this data very carefully, there won't be pointers there. So that leads to the idea that if I allow the laying out of memory freely, when the actual laying out of memory cannot be cluttering memory that contains pointers or array descriptors, which we haven't talked about yet, then this careful laying out of memory cannot be used to forge pointers that can then be used to take over the system. So we're going to get into it more, but an important mechanism is array descriptors. Of course, C doesn't quite have a notion of arrays as the simplest notion of arrays possible. But arrays have always been kind of a hack on top of C. And variable length arrays and runtime dimension arrays were added in C and C99. And Dennis Ritchie had said that he didn't like the proposal when that proposal was tried to be put into C and C89. There was a McDonald proposal, the GCC proposal. And it's basically a proposal where it leads to programming errors. So you might have a function. This marker is really tight. You might have a function that receives an array. And well, let's just say we're using ints. So you're passing the dimensions that dimension this array as arguments. That this is kind of how you do it in C. And you could pass them out of order and nothing checks this. So it's easy to make programming bugs when you're doing these variable length arrays. Actually, variable length arrays in C are used so infrequently that it's become optional. In C11, variable length arrays, you can say whether you support them or not. And most people walk away from variable length arrays and they tend not to use them. So they were done poorly. Dennis Ritchie protested in C89 and they snuck it in anyway in C99. And arrays are done differently in this language. And because the goal of the language is to help re-engineer large C code bases that are system software, that are operating system parts. It's not to re-engineer some C code that came from Fortran, that got rewritten from Fortran into C. That's not the goal. Then a better approach to arrays is required. So this is the idea of array descriptors. So array descriptors are, go ahead. Yeah, so we're going to get to that. So yes. Yeah, so in this presentation, we're just going to talk about what you're doing computationally within a C address space and to implement, let's say, a kernel. But the reality is that sometimes you're talking to coprocessors or to GPUs or some other things that do work on data. And, I guess you might have an array of low precision floats that you're giving to some GPU to do AI or something else. And well, you're pointing at the memory and you're going to give it to some device. And this device might, have direct memory access and affect things. In that kind of a world where you have devices unconstrained affecting any amount of memory, they themselves could be corrupting memory and corrupting pointers and whatnot. So that's a separate thing to address outside of the language. But so let's table that discussion maybe for offline.
So does this eliminate pointers?
No. The language has pointers, has to have pointers. Absolutely, yeah. We're going to look at a lot of code snippets in a moment. So anyhow, so we're going to talk about array descriptors. Array descriptors are implemented by the language, and an array descriptor describes, they're pointer-like, but they describe one or more objects. And they also, if it's a multi-dimensional array, they also describe the dimensions of the array and the maximum the number of elements in each one of the dimensions, but they're kind of pointer-like. But an important property is that array descriptors, when you assign into them or you fetch from them, that assignment and fetching into an array descriptor is atomic. And that has to be implemented by the language. You cannot say you have a global array descriptor. Say it's a unidimensional array. So a unidimensional array descriptor is just a pointer to where the data is and the size, the number of elements. Well, that's 2 words in most machines. It was a native instruction. You cannot load atomically 2 words or store atomically 2 words. You have to do maybe a compare and swap or something else to atomically load them and store them. But the idea is the language and guarantees that loading and storing an array descriptor is going to happen atomically. You're not going to be assigning one array descriptor that points somewhere else with a different number of elements into a pre-existing array descriptor and end up for any amount of time where it can be seen concurrently by another thread or by an interrupt handler or anything, where you have the original pointer with a new length or the new pointer with the old length. You cannot see a half-updated array descriptor. Updating multidimensional array descriptors is a bit trickier, and it's like a technical discussion. Let's not get into that. Anyhow, there's a family of cast operators, and we're going to talk about that too. I just wanted to mention them, but we have the cast that is as close as possible to C, but you'll get compile errors if you're doing something unsafe with that cast. There's a try-cast, and there's a U-pointer cast, and upcast to go from a base class to a derived object. If the pointer to the base object was really of the derived object, then the upcast will succeed, otherwise it'll fail. And of course, you'll need an unsafe cast, where you're basically telling the language, no, trust me, because I'm implementing the memory manager for the language, or you're doing something else that you have to do unsafely, right? So you have to have some amount of unsafeness to implement the allocator of the language itself. Okay. Now, another insight in this discussion is that there's really 2 kinds of data. There's plain data and non-plain data, and this is my definition for this language of what it is. So plain data is data that nowhere contains pointers or array descriptors or variable length arrays, or there's this new type called index and uindex. It doesn't contain the variables of that type, index and uindex. And let's ignore the index and uindex for a moment. It's not particularly important. Now, an object of a user-defined class, even if it doesn't have pointers inside of it, is not plain data either. So in this language, well, you have struct for C compatibility, and you have class to declare user-defined classes. Struct and class are not unified. Struct is a thing that comes from C to be compatible with C, to lay out memory, kind of, the low-level way. And class is because you're defining a user-defined class, and you're going to create objects of that user-defined type. And all of the objects of the user-defined type are, by definition, not plain data. Even if it's just 2 floats that implement this class, it's still not plain data. That's the definition. Well, the non-plain data is the opposite of that. And so let's, okay, now we're going to switch to another. Now we're going to go through quite a few things that show a flavor of the language. So I'm going to go through some of the, like a brief language overview, and then we're going to get into the safety aspects. So I have different slides for that. So anyhow, just to get a feeling for the language, of course, you got to start with hello world, right? But before we start with hello world, let's start with a class. So here we have a class, and this might look a bit strange, or it might look very familiar. But, well, it's a class. The name of the class being declared is stack. This language has a notion of contracts, kind of borrowed from Eiffel. So whenever you declare a function or a class, you can actually make some promises. And you're saying here, when I've constructed this object of class stack, I'm going to promise that it is empty. I'm constructing a class that's a stack. The stack will be empty. So this promise is going to be verified at the end of an object of class stack when it's constructed. Now this looks kind of like a function, and in a way is a function. And what you have at the top, until that return, actually the whole thing is a function, but it's a class and defines a type named stack. And the things that you see with pub, priv, or prot, you don't see any with prot here, there you're declaring members. You're either declaring member data or you're declaring member functions. So we're declaring some member data. Because we want to be compatible with C, const cannot be used to declare constants as in C. So lit is to declare a literal, is to declare a constant. So you're declaring a type constant. Max int is a constant of type integer, is a literal, and it has the value 100. And here you have two other members that are private, an array of that number of entries and a pointer to the current stack pointer, and it's pointing at the base of the entries. And that all looks very much like C. Now the constructor itself is code, is being run, and the members are, the data members are the ones that are declared there that look like data. Those, let's make sure I don't fall here. Those first three things, they're data. One happens to be a compile time constant, these other two are data. And idiomatically, this is a function, and if you didn't put a return, it would keep on running down. These are the members of the class, these are member functions. And idiomatically, you put a return there at some point to say, hey, don't keep on looking, there's no more constructor code down there. But then you have a few other functions. You have a member function that says whether the stack is empty or whether the stack is full. And you have a push member function that has a requirement that the stack not be full. And if the requirement is broken, then you're going to get an exception because you try to push into a stack. And in this specification of this stack, if you try to push into a full stack, you get an exception because you're breaking the contract. The push member function requires that you call it on a not full function. And you have the pop requires that the stack not be empty. You're going to pop something, and it promises that the stack won't be full because if you pop something, it won't be full after that. And you have the top member function that returns the element at the top. It also requires that it not be empty. Anyhow, the code all looks very much like C. Everything that you look in there that looks like C and C pointer manipulation is exactly what you expect from C. Go ahead. Oh, -1, you're indexing from a pointer negatively. So you're basically doing pointer arithmetic. That SP square brackets -1 is exactly in C the same as star SP -1. You're saying wherever SP points, the word before, get me the value there. It kind of looks weird, but that's C. That's C and C++. Yeah, so it's saying that when you've constructed an object, the class is promising that that stack that you just constructed is empty because you haven't pushed anything into it, and it's yeah. Well, this is a toy example for a book. Yeah. So by the way, this set of slides that you're looking at now is exactly from the book that has been written. I took out all of the surrounding text, so not to make it too distracting. I just wanted to briefly, and we might come to refer to it. I have also here the book itself that's been written, and it has a table of contents and many chapters. And basically, for this presentation, I chose to not go through all of this verbiage, right? So that we're seeing in the other file is the same thing here. I just took out all of the surrounding stuff just to show code snippets. But you can download this stuff today if you want to and go look at it. You can look at the book with the code and all of the description of the language. I haven't uploaded the thing with just the code snippets. All the code snippets that we're going to talk about are in the book. They're from the book. Anyhow, this is a toy stack. It's not a great implementation of a stack. It's just to show a stack. Okay, so that's a good question, right? So if these requires and these promises, and within the body of the function, you can also say assert. You can also say expect. Of course, a compiler is going to be verifying these expressions, and the compiler can actually maybe make decisions from these things. So if you have a require that some variable be positive or that some variable be greater than another, the underlying C compiler can see these things and maybe make optimizations based on that. So I'm not well answering your question. Maybe you can tell me where you're leaning. Where are you going with this question? Excuse me? Yeah. Yeah, so this language compiles into C. We rely on the underlying C compiler. Yeah. Yeah. At this time, no. But that's an interesting thing. And we have one more here.
Because it sounds to me, the one that is correctly, it sounds to me like saying that Google has no runtime other than whatever code generates in line with the code that.
Yeah, I didn't say that it did not have.
No runtime.
I didn't say that it did not have a runtime. Well, yeah, if pretty much, I don't think there exists a single language that doesn't have a runtime. You know, there will be some very low level things to do memory moves when you're doing structure assignment.
You have, besides that, we also have some library that has to be.
That must be there? No. You can do your own allocator and not use the allocator code provided, for example. A large runtime? No. Well, you always have a bit of, that's what I mean. You always have a bit of glue code to implement structure assignment. Do you inline that? Well, the C compiler itself will have some C runtime, etc., right? So maybe some weird calling convention thing or something else might have a runtime. Excuse me? Well, so this is not a language for self-modifying code, so no. But if you have function pointers, you're going to replace your function pointers with whatever else you want them to point to, right? As you would do in C. Okay, so anyhow, this is just to get a bit of a feeling of that. And well, if you were to use a stack, it's of course all going to be look very much like C or C++. So you have a stack, you're declaring S is a stack, and star P is a pointer to a stack, and you're assigning it the address of S. And well, you're pushing 7 into the stack named S, or you're popping it via the pointer. And you can actually go access that literal 3 different ways, via the object S or the pointer P, or actually the class name, because it was a literal. So in a way, a literal, you don't need to have an object to operate on to obtain it, right? It's a constant. So now let's look at hello world. And hello world, of course, when you're throwing away things from C that are unsafe, you have to throw away printf. You have to throw away bar args. And of course, bar args and printf, they come all the way from BCPL, which was a typeless language that became B when Ken Thompson re-implemented it. And if you go find yourself a BCPL book, you'll see, oh, this is where printf comes from. This is where scanf comes from. So none of those things are in the language because variable argument functions are not safe, kind of by definition. So here we have 2 hello world programs. One is, well, within the namespace where the live C stuff is, called putS, and I put a string there. More interesting is the second one, that given a string, I'm going to call the member function print on the string. So in this language, you have native types, and you can actually add member functions to native types. And this is how we solve, without building it into the language, how we solve how to do formatted input and output. Once we've thrown away formatted input and output, how are we going to do that? Of course, the solution to have type safe formatted input and output in C++ is operator overloading. We don't have operator overloading because that's a mountain of complexity I don't want in the language. We'll talk about object-oriented in a moment. But let's just look for a moment at how do you do formatted input and output. So here we have 2 pieces of code. Well, one is the C version of this stuff. that is printing the temperature in Caracas and is doing some arithmetic. So the second one, you should recognize the output of both is at the bottom. The top one is the one in COOGL. So what this is saying is, on a list of expressions that are delimited by semicolons, on each one of those expressions, call this member function on them. So that means that this string called print on it, and on this float called print on it, and on this other string called print on it, and on this object, which was C, which I guess must have a member function that was added format, on this object that this returned called print, and on this other string called print. So on is a syntactic sugar that says, on a list of expressions, call a member function. And the language doesn't know about input and output, but has its on expression. Instead of print, you could have said scan, and that's how you would do scanning. Now that code there, if we remove the on expression, would look like this. So an on expression is what I just said. Basically, you just call print on each one of these things, and this is just, of course, much uglier. But this is the way you do type extensible input and output. You can say extend class int, open curly brace, and add a print member function to integers or to a string literal, etc. So basically, you can add member functions to the native types. Hence, you can add print and scan to them. You can add, of course, member functions print and scan to your objects, and hence you have a type extensible input and output without building input and output into the language. And let's just skip. Well, this is an important one. I didn't delete all of the text here because this is a really important thing. There's a schism between the compiler writers and the users of the compilers, the C programmers and the C++ programmers. And this is, to me, the schism about undefined behavior. When C was first standardized, it was put into the standard this thing that says, well, some things are undefined behavior. And undefined behavior was meant to mean one of three things. One, the compiler generated the most appropriate code for the machine. Or two, the compiler gave you a compile time error, and you have to deal with it. Or three, the compiler got a bit confused and didn't know what to do. Maybe it produced wrong code. Now, that third one, the second and third generation of compiler writers, decided to say, oh, wherever the standard says undefined behavior, I can go engineer my compiler, find undefined behavior, and then delete that code. Hence, my benchmarks will run faster. So you'll see like people like Intel were caught with their, sorry for the bad expression, with their pants down. They were tuning their compiler so much that they would be so fast for spec-int and spec-fp, but it wouldn't even, the programs wouldn't even run. And Motorola, the PowerPC team, found them and said, hey, yeah, you're compiling this, you're going so fast, but when we run your compiler with the spec benchmarks, you're not even producing the correct output. So that's what people were doing. So it came to be written into the standard that, oh, signed arithmetic is undefined behavior. Because on some machines, signed arithmetic overflow is undefined behavior. On some machines, we're going to put in the standard that it's undefined behavior. And as soon as that got put in there, nothing changed, nothing got broken. There were millions and hundreds of millions of line of code that kept working. But 10, 20 years later, some compiler writer guy said, oh, if I see something like this expression, I see let's make sure I don't fall here. If A plus B is less than A, and these are A and B are integers, and somehow the compiler can infer that they're all positive, not zero, then GCC first and Clang later said, oh, I'm adding a positive integer plus another positive integer. How can that be less than the first positive integer? Oh, this is undefined behavior. The compiler will delete the code because the only case where this would be less than that is if there's a signed overflow, as in how the hardware works. If the hardware overflows, this will be less than that, and this is a lot of people wrote a lot of this code to check if something overflowed. Now these compilers will go and delete all of this code. And maybe this was your code that was going to make your kernel secure or some other thing secure because you were checking for overflow. And these compiler writers decided, oh no, we're going to make it faster. You're confused. You programmer, you're confused. I can do whatever you want. they produce no code, zero code. The if is gone, everything is gone, the body of the code is gone. Well, basically, in this scenario, well, okay, they'll do it as if you compiled it if false, right? Yeah. So you are correct. Yeah, yeah. So basically, they'll compile it as if this was always false. Now, well, there's this little language in the standard that says sign arithmetic overflow is undefined because there happen to have been maybe some machines when the standard was written where that wasn't undefined. Every machine that exists that is alive today has 2's complement from the system 360 forwards, and signed arithmetic doesn't trap, is not undefined behavior at the hardware level. Signed arithmetic overflows under the rules of 2's complement. So what would have been a good implementation of undefined behavior on machines that have 2's complement? Just generate the instruction. Actually, the instructions for signed and unsigned addition and subtraction are exactly the same in all of these machines. Sure. Yeah. Yeah.
First of all, overflow of the hardware level is very well defined. There's no differences are whether overflow is first an exception or not. On most modern hardware, we throw away the notion on 70 instructions said the overflow is throw an exception. So that's
no. Okay.
So we're not going to go there now. So the other question is, what does the compiler do? Does the compiler generate code?
Yeah. Yeah. So
that is the part that is undefined because the time the standard was written, there were already too many compilers that had different behaviors.
No, and the reality was that when the standard was defined, there were maybe some weird machines that were not 2's complements, the Cray machines that were still. Yeah, the Cray CDC machines did not have 2's complement. They had 1's complement. So let's cut this conversation short. When the standard was defined, there was an umbrella for weird machines. None of those weird machines are alive today. They're all dead. Okay, but we have to move on. Yeah. So basically, this is a language for existing machines that exist in the real world for the current architectures that live today. This is not a standard that you could. This is a language that is not meant to be retrofitted onto, PDP-10 with 36-bit words, and where the Cray was signed with 1's complement or something else. So this is for a very real problem that exists today for these large code bases. And the idea is we have to tackle this undefined behavior problem, and it's a growing problem. And there's a very smart guy who was the guy who did LLVM, who was kind of, you could say, the father of the Clang compiler family, and he wrote this thing about undefined behavior in a paper that a blog or something that says what every C programmer should know about undefined behavior. And these are the things that scare him, should scare all of us when you're having your C code and your C++ code. It works today. Compiler changes, your code might not work with a new compiler. So, there's no way to determine if a large code base contains undefined behavior. And you can all read it by yourselves. But at the end, he says, given that there are lots of bugs in real application and that C is used for a broad range of critical applications, this is pretty scary. Basically, the point is, as soon as the compiler writers go wild and they decide to rummage in the standard, anything that says undefined behavior, they're going to use it to optimize code. To me, it's fine. If you compile something that says undefined behavior, give a compile time error. At least give a warning. Don't just make the code disappear or make the code do weird things. So that is C and that's C++. And all of these kernels compiled today because they turn off all of this undefined behavior optimizing things. If you look at the flags used to build any of these kernels, you will see everything that gets turned off. Now,
This guy writing a language that doesn't even meet basic rules of standardization. It's changed Swift so badly that the original shipped version of Swift doesn't actually compile on the current version.
Yeah.
And there are people who ask this person.
yeah. So anyhow, the point is, C has this problem. C has a problem, and C++ have a problem where the compiler writers are not trying to serve the community, they're trying to serve themselves. They're trying to make their things go faster under some benchmark, but if they're breaking code, it doesn't work. So what happens is, for the benchmarks, they'll add the flags, they'll add all this stuff, but to keep Linux and keep all of these code bases working, they'll add the flags so you can keep on adding the flags to turn off all of the craziness in the compiler. So anyhow, this is a schism. Most C and C++ programmers have issues with what these people are doing. If you look at what they've done with Shift, it's kind of... so anyhow, if you follow this discussion, and if you look at it in the book, I'm not going to go into detail, they talk about as if the C language designers wanted to get ultimate performance. No, the C language designers, Ken Thompson and Dennis Ritchie, wanted to rewrite their assembly Unix into C. They did not want ultimate performance. They just wanted it to be good enough. If you go read the historical aspects that they wrote about, I put all of the quotes, but you can go read. Basically, they wanted it to be expressive and efficient to have completely displaced assembly language programming on Unix. That was the goal, not to make ultimate performance, right? Anyhow, there's a lot of historical references in there. Let's not go down that rabbit hole of undefined behavior. The language I am working on does not have undefined behavior, does not produce code does not produce C code that can be seen as undefined behavior. Or it calls a compiler in a way where it turns off the stupidest things that the underlying compiler is doing about undefined behavior. For example, it's passing the flags down that say integer overflow is not undefined behavior. Integer overflow works as the underlying machine works, which is 2's complement. And actually, there's even a movement in C++ standardization effort to try to standardize that actually that's a behavior of integers. So C++ might come that way. Now, just a little nit. This is like a little pet observation. Somewhere in the Stroop C++ world, they started tacking the stars on the left. And actually, what you see in the top, if this was the C# language, both P and N would be pointers. Hence, putting the star stack on the left, tacked on the left, in C# makes sense. Both P and N are pointers, but in C, and COOGL, and actually in C++, you shouldn't put the star on the left because the star belongs to P, doesn't belong to the int, and it doesn't belong to the I. So somehow that disease got into C++ for some reason. I don't know how. Yeah, but that became kind of what people do in C++. Yeah. Anyhow, let's ignore that for a moment. About complexity, obviously, you can go read these. There's some notes and quotes from Stroop himself about the complexity of the language and what Ken Thompson had to say. But the worst part of why C++ has become so complex is that this stuff here that you see comes from a paper and comes from the book from Stroop, his 4th edition of the book. Everybody reviewed it, him and all of the C++ gods. And this code presumably was supposed to work. Everybody reviewed it. Everybody believed that it worked. And actually, it doesn't work. Some tool found that this code doesn't work. Sadly, it's quite ironic that they meant to assert that I have heard it works only if you believe in it. But actually, this code does not work. They changed C++ and C++ 17 to actually specify some of the order of expression evaluation so that this kind of code would work. Because people have been writing this idiomatic code that kind of happens to work by accident. So if you have this kind of code in C++, move to C++ 17. At least it'll work reliably then. But anyhow, when you have a language where you write examples in a book and everybody looks at them and says, oh, this is correct, and then a tool finds that could be compiled incorrectly, there's too much complexity in there. Anyhow, there's a few sections in here. I'm not going to go down into it. You can read it in the book. Okay, so let's skip all of this stuff about the subset. The subset, I kind of described the subset, but the book is kind of self-contained, so it describes the language itself. I'm just going to skip through all of these snippets. and get to the next chapter here. Okay, so let's talk a little bit about array descriptors, tuples, and literals. Again, I only left the chapter names and the abstracts here because I thought they were cute. Maybe you guys can read them while I bore you. But you should read this book just for the quotes. They're great. So this chapter talks about array descriptors, which are key for making the language safe. And it also mentions briefly tuples and literals, which are the way to declare constants. You can say a literal is like a const in C++. You're declaring a type constant. So let's talk about array descriptors. So, well, an array descriptor is an object or a thing managed by the language. So if you have an array, even a classical statically dimensioned array like A there, it happens to have these members called max, and which is also like a little array. And max is an array which has as many entries as the dimensions. So this array A has 2 dimensions. And this member of A that is kind of synthesized by the compiler, it wouldn't exist in memory in this scenario because it's kind of knowable by the compiler. But sometimes these things exist at runtime. But in this scenario, A.max0, this is the number of elements in the first dimension. A.max1 is the number of elements in the second dimension. And A.start is a pointer to where the memory of the array is. And A.end is a pointer to the last element of the array plus 1. Because in C, you have these open ranges where start points at the first element and end points 1 past the last element. Yeah, it's kind of idiomatic. Yeah. So start and end, you have an open range, end is 1 past the very last element of the thing. So let's look a little bit at array descriptors. So, well, here you have, I'm just going to scroll them to the top. Here you have a global array tab with 10 elements, and in this function f, I'm declaring, it has an array descriptor called desc, and you declare the array descriptor like this. Now, this is no longer C code. This wouldn't compile as C code, right? But you're basically saying this array descriptor refers to that array, and through desc, you could access the number of dimensions. You can get to the data. It's as if you're pointing at that array, but it knows all of the dimensioning stuff. So here we have the same example where you're grabbing that array descriptor, you're passing it to a function, and in C, when you pass the name of an array or the name of an array descriptor, it kind of stands for a pointer to the first element. So all of that stuff is the same. So here, this increment function is saying, okay, I'm receiving a pointer to the first element of this array. The function increment only knows about one element that it points to, and it's saying, whatever it points to, increment that data item, that integer there, the first element of that tab array. So let's look at a bit of more examples. So, so this second one here where it says last 5 is the address of the element at 5. This is creating an array descriptor that starts at that element and it goes through the end of the array. So it's like a sub array of it. And and here you have another one is doing exactly the same thing. These 2 array descriptors refer to the same data. All of these guys are referring to this tab. They're array descriptors pointing at different places in there. Now, here you have more like slices. So here we're saying I have an array descriptor first 5, that is the address beginning in the first element up to and excluding the last, the element number 5. So the first 5 elements. And here it would be, beginning in element 5 up to element 10, but there really isn't an element 10, is excluding the second one. So this lets you create slices, This array descriptor points to some memory within another array. There's no sparse gathering fanciness. No, this is as close as possible to the machine. It's meant for C guys not doing numerical stuff. Some older languages had that stuff, but this is not one of those. Now, when you have an array descriptor, you can do all of these ways to walk the array. You can walk it with indexes, forwards or backwards, or you can actually walk it with pointers. And the reason I'm showing the walking it with pointers is that in the old days of C, where you had segmented machines with segment registers 286, x86, and maybe some other machines that are all dead now, walking an array backwards from the last element not in the array, decrementing the pointer, and stopping when you get to the, and continuing in the loop while you're greater than the pointer to the first element. This would be undefined behavior in C, because in a segment machine this might go crazy when it goes when it points before the memory of an array. In reality, in all of these flat address space machines of the real world that I'm worried about, this is defined. This is all well-defined behavior. And the way this is done, the underlying C compiler won't be able to see what's happening. So it's not going to mess it up. Now, if you had an array descriptor, you have a function here that takes an array descriptor with these dimensions. When you receive such an array descriptor, notice that there's no arguments passing the values as in C99 variable length arrays. But you can just write your 3-level nested for loops using the max values, and then just work on the elements and the array, use them. Or you could just say, I'm just going to work on all of the elements sequentially in memory, starting at the first element all the way, stopping before the last one that is not in the array, and then I just use them. So this all looks very C-like. Now the array descriptors, of course, are not C-like. They're fancier, of course. And not to go very slow on this, but there's some more examples with array descriptors being initialized, and that's how the memory would be linearly. That's how some of these subarrays would be, and let's not stop on this. So, but anyhow, if you go through the book, you will see how these subarrays are referring to sub-chunks of this multidimensional array. So let's skip that. Now, so beginning to approximate things that relate to language safety. I should probably keep a look at the time. Oh, wow. No. Yeah, so you can take a slice of a multidimensional array descriptor as long as you're referring to contiguous chunks of memory. So not arbitrary chunks. It needs to be contiguous. So it's not very useful for fancy, weird math. Yeah, no, but it's not. It's just contiguous chunks of memory. But we're running a bit slow, so I'm going to start skipping on questions and just try to move a bit faster in this. So anyhow, when you have an array descriptor, the array descriptor is either going to live in global memory. Global memory is addressable by concurrent threads, interrupt handlers, signal handlers, exception handlers, whatever, coroutines. So array descriptors in global memory, the only thing you can do with an array descriptor that is in global memory, or that the compiler cannot prove that it isn't in global memory, is fetch them and assign them. You cannot actually index an array descriptor that is that is global. So what you have to do when you're going to access the only time you can index is if you've copied that array descriptor as a local variable, and then you can do the indexing. So the only thing that needs to be implemented with respect to concurrency is that these global array descriptors that I call them restricted, is you have to be able, the compiler has to generate code so that they're fetched atomically, and when they're assigned into atomically. But, excuse me? Oh, so basically here, say you were going to assign the value of B into A, so you fetch it into something in memory on the stack that no other thread can see, and then you atomically store it here. So assigning one array descriptor to another, it's as if you did that. Yeah, no, yeah. Oh, no. If A had a prior value, what this guarantees is that if somebody's concurrently fetching A, they're going to see the values before or after, but not a mix of both. Okay, so let's skip this. Well, if you access an array out of bounds, you're going to get an exception. So this function here, ran val, that's going to throw an exception if the random indexes are outside of the dimensions. And let's not dwell on that. And let's skip this. Well, so that's, so when you have a language and something happens that is wrong, you have to raise an exception. There's no other choice. You're over-indexing an array, you're under-indexing, you're dereferencing a nil pointer, or you're doing something invalid. You're calling through a function pointer that is set to nil. And you want an exception to happen. You want exceptions to happen reliably. You don't want the compiler to say, oh, using null is undefined behavior, I'll delete the code. Right? So that creates a problem with null incompatibility, and hence nil, and we'll talk about that in a moment. But here we have an example of what kind of code would the compiler generate. So the code at the top is kind of going to loop on an array descriptor until it finds a 0 and, I don't know, add them up. So, well, you write it as in C and you don't put any bounce checks. You're going to straddle through memory, and in C, we just maybe stomp on some neighboring memory. And in reality, when this is compiled as C, COOGL, then the array descriptor that you pass in as an argument with A in square brackets is going to be received, the value of the array descriptor is going to be received in 2 arguments, a pointer into where the data is and the first dimension of that max field. Now, notice that from a source code compatibility, this code is exactly the same as in C, because this in C is a valid declaration. This would be as if you declared int star A. This is a synonym for a pointer to an integer. So this is exactly C code. If you compile it as C or as C-lean with a C compiler, well, you might stomp over memory because it's not being checked. But when you compile that as COOGL code, then you're receiving the array descriptor properly, and the compiler is going to generate some bounce checking somewhere, and it'll raise an exception if you try to access memory beyond it. So we're going to get to that. Sadly, that's...
May I make one comment? Given that arrays in C are zero-based.
Yeah, and its language are zero-based too?
Yes, the easiest and most efficient way to avoid array bound overrides is to, because if loops are specified, loops start or scans start with 0, start them from the opposite direction.
Oh, you have to do the loops in the order the programmer says.
You don't have to check
Oh, no, of course. The point of it is in this scenario, yeah. So anyhow, we'll hit into things that maybe relate optimization at some other time, but we're going to talk about concurrency if time permits. Let me not digress into that now because we're really pressing for time. So here you have a well-behaved loop that is saying, well, add all of the elements in the array, and the compiler can see that you receive the array descriptor as an argument. Nobody can change it concurrently under you, so you have this thing that is not moving under you. So it's going to work on the base of the array, and it's going to walk it while it's less than the end, and it's going to sum them. This by itself will not produce any bounce checking because the compiler is seeing that you're actually walking the array descriptor safely. So that wouldn't generate any extra code. Well, it's seeing that you're basing the pointer walking on the array descriptor. If the array descriptor was passed to you by construction, the array descriptor is well formed. It refers to the memory. So the memory that you're walking, you're not walking it outside of the indexes. So it doesn't, you're already checking that P is less than N here. So, right, so this is the ending condition. So it's not going to go past the end of the array. Yeah, in that scenario, it wouldn't be needed. Yeah, well so yeah. Yeah. Also, so that's a good example. So I actually have one like that. So anyhow, we're going to get to the safe chapter. Here, I was just trying to show tuples for a moment. I was trying to show array descriptors. Yeah, it's a language feature. Now we're going to get into. Yeah. So sometimes you point to a string, and the compiler will actually produce the array descriptor for it. So this little function that is indexing, moving this p pointer within the thing that points at dog, that has an implicit array descriptor, and all of that is checked. And in this scenario, is returning the g of the word dog, and that's all safe, right? You don't actually have to have written an array descriptor for that scenario. But anyhow, let's look at tuples. So a tuple is a thing that kind of looks like a structure, but it also looks like a series of assignments of default values, and they use square brackets. And in this scenario, there's a bunch of examples all here rolled into one, but we're type defing this tuple, which is a keyword, which has, well, the tuples usually have two or more, just to make them useful, has two or more members. In this case, it's a file descriptor, and it's an error number, and you can give them a default value if you want to. And this is a new type that we've defined. And here we have a function that does an open, it returns a tuple. So returning multiple values is a quite useful thing in a programming language. This language returns multiple values. You can read all the details, but if you have like a naked return, then the tuple with the default values, -1, and the error will be returned, or you can actually manufacture the values to be returned here, no error in the file descriptor, or you could just, manufacture some other error in some error number that you picked up from somewhere else. So tuples are a way of returning multiple values. Quite a few languages have had tuples. But somehow they haven't become mainstream in either C or C++. I know that in C++ you can do some template, well, not natively in the language, maybe with templates, right?
No, tuples are part of the standard library.
Yeah, so it's not built into the language, right?
Well, they have structured bindings.
Yeah. Yeah. So anyhow, the point of tuples is that quite often you pass arguments, and you pass the address of a variable as an argument because you want to get a value out of a function through an argument because you're already returning a value. So tuples are a way of avoiding that. Now, tuples don't give you some magic thing. Like if you try to do an assignment of a tuple to another, that's not going to do a swap. It's unspecified. It's not undefined behavior. There's a difference between being unspecified and being undefined behavior. Anyhow, literals are a way of doing constants. If you had written const, this would be C++ for constants. Well, you're going to have to read the beautiful quotes yourselves. Here's the same stack, the same class we saw before. Okay, so here we have an interesting thing. We reach 8:30. We have half an hour. We can skip a lot of the language details and go into what makes it safe, which is kind of the interesting discussion. Or we can see more of the flavor of the language. Yeah, so I think safety is kind of the selling point, so we should probably get into that. So there's a lot of explanation, and at the end you have to actually implement it correctly, right? We're not going to prove an idea. Okay, so let's go there. So let's actually do a few things on the whiteboard just to set up the thought process behind this. Yeah. So that's so basically the explanation of what is safe is a bottoms-up approach. How that's defined, but this red was a bad idea. So let's not use red. Well, I lost red, so. So what? Yeah, I know, right? So unsafe Well, how do you define safe that it is not unsafe? So what is unsafe? If you're allowed to make memory accesses that in a way defeat the type system so that you can exploit that defeating of the type system to take over the program so that the program does things that it was not meant to be done. Another way to look at safety is this. If you wrote your code in the language and you hit a bug, or an exception gets raised, or you go through a nil pointer or something, and the program crashes, you can debug the whole thing just thinking about the program and looking at the data at the programming language level. You don't have to drop down to the machine level because the stack got corrupted, because some function pointer got smashed and you jumped to some arbitrary place and ran some arbitrary instructions and then crashed. So when a programming language is safe, you can debug everything at the programming language level, never at the assembly level. So it means you cannot forge pointers. If I have a pointer to something, you cannot go and at a later time, that is pointing to a thing of a different type, and the earlier pointer survives. So now you have an old pointer and a new pointer with different types, and you're accessing through these pointers some memory, and you're smashing memory. Yeah, exactly. So you cannot do arbitrary things. You have to do them carefully. I'm going to bring this other thing so I can have my notes. Well, you should all go read the quote about safe programming, but I won't make you do it here. By the guy who wrote Quicksort, who designed Quicksort. Yeah, I don't think he actually was the first guy who had the idea of having a dummy value for a pointer that points to nothing. So maybe he's thinking he invented and all, but people have been programming probably 20 years before that. So. Yeah. So anyhow, let's look at first at a few examples of things that are in C that most C compilers might not catch. Some of them might. That are bugs where you're smashing memory. So before you can actually try to fix C, you have to show some examples of things that go wrong, right? So here you have, well, this first function has an array of one element, and it tries to access element 200 and assign an X in there. Now, we do this with a straight face in our programming languages, and nobody calls us. It would be as if you get into an elevator and you can go up to 4th floor and you punch 100 and it shoots through the roof. Or you say, I'm going to go to minus 70 and it smashes, right? Because it's only one basement. So these are mission critical systems, and this notion that we're not even going to check indexing is mind-boggling, right? So of course, the first one would, well, that would be caught by the compiler at compile time, but let's look at them. They're becoming more and more interesting. So here we have, you receive a pointer. When you have a pointer in COOGL, you can only access the data that it points to. You cannot do pointer arithmetic. You cannot access 100 elements past it because it doesn't know whether there's an array there or not. It doesn't know whether there's valid data. So they store 1 at index 100. It's also unsafe, but you can do that in C and C++ as well. Yeah, there's no bounds information, right? So the idea is that when you're specifying pointers with star into a function, it's a pointer. You cannot do pointer arithmetic on this guy because you don't know whether there's neighboring data. If there's neighboring data, then you pass an array descriptor, then you can have a pointer that points within the array descriptor, and you can move your pointer around within the array descriptor. The compiler will be watching that you don't step out of it, and we'll see some examples. Well, you have, of course, the use after free, where you malloc some memory, you free it, and then you go still use a pointer and stomp the memory. We have, well, so here we have this stomp where it's, stomping on the null value after the HI, and it's putting an X there, and you call string copy, and string copy is going to run crazy past the end of S, and go touch some random memory. Now you can smash memory through a pointer. You can have a union, and you can have the pointer within the union point to a character, but then you can, through the union, assign to an integer 17, and now the pointer maybe has the value 17 in some part of the pointer, and you try to dereference it, and you're using a smash pointer, and this is all unsafe. Now we have more subtle problems like this one. Here you have a function bad that, so the function bad declares a local variable, and it's calling that function set on top, passing the address of it. And whatever set returns, bad will return. Now bad knows that set will actually set the pointer that you pass and return the same pointer. So in a way, it's not visible really without looking at the code of set. You don't know that bad is returning the address of C. So the caller of bad, maybe main call bad, it returned a pointer to this thing that was on the stack, but bad has already returned. That's crazy. And now you go store on it, and you're probably smashing your return address or something. All of that's unsafe, right? Now, even that example is not so unusual because it might look like it's contrived, but in C, you could have used a string char. I have a buffer on the stack. I call string char with the address of the buffer. String char returns me a pointer within the buffer where it found a character. If I return that pointer to my caller via string char, I'm being evil, and I'm returning addresses of stuff on the stack that are no longer there. So all of these problems are addressed by the compiler and by the language in the presence of separate compilation, even separate compilation across modules. And sadly, there's not enough time to get into that. We talked about plain data and non-plain data. A very brief note about index and uindex. These are indexing types. We write a lot of our code, and our indexes are written with int. You can still run your loops with int or some other type that you prefer. But if you're putting indexes into data structures and you're using them to index, well, these indexes, if they get smashed because you're smashing half of them, and while they're being accessed, then makes a compiler and the language work difficult. Also, we're kind of crossing from 32 bits to 64 bits. There's a lot of dusty decks of code that access arrays with integers. Well, soon enough, every machine has many gigs of RAM. And if I have a half of a terabyte machine or a 64 terabyte of RAM machine, my ints are kind of small to index my arrays, right? Because they're 32-bit indexes. So having a type that is used for indexing is better while people move away. So kind of this language has these index and uindex types. And anything that is of those types is not plain data. Now, here's some examples of plain data, and I kind of described it before. This all looks exactly like C. So all of these are plain data. They have, they don't have pointers within them. Oh, sorry. So these are non-plain data because they have pointers. Well, so if you use index and uindex, then they're not plain data. If you just use size off or some other type, if you use ularg, if you use some other unsigned type or any other type. Sadly, we have so little amount of time, I'm going to have to cut you off and move on. And sadly, I'm not going to even think of answering that question because we have so little time. So we got to move on to the subject of the class. So sorry about that. So anyhow, so this would be plain data. There's directory entry, classical Unix directory entry. All of these are plain data, right? Stuff that you're going to put on disk because you're writing a Stone Age file system like the original Unix file system. Now, let's talk a little bit about this cast and this try-cast. So say you have a pointer to an integer, and you want to cast it to a pointer to a character. Well, that's always safe because we said integers are not, they are plain data. And if I cast a pointer to an integer to a pointer to a character, well, it always fits. The character always fits in there. Now, if I had a pointer to a character and if I tried to cast it to a pointer to an integer, then it would smash the surrounding data. Nobody's guaranteeing me that that's a valid cast, so the compiler is going to give you an error there. Now you have this this try cast that will let you do it if it is safe or not. So we're going to see into that in a moment. We talked about external memory and whatnot, so let's skip all of that. Well, so one of the restrictions on the language, by definition, unions cannot contain indexes, pointers, or array descriptors. It's out of the language. Just keep it simple. So this is a very interesting one, and it's actually very well defined and very important. Global memory cannot ever point to memory on the stack. And some kernels will do hacks to point to memory on the stack from global memory when they block threads or whatever. That's not allowed. Global memory can never point to memory on the stack because it makes a problem of functions returning untractable and these global pointers pointing to data that is no longer valid. So by construction, if you were to read all of these rules, the language does not let you set a global pointer to point to data on the stack. And there's quite a detail about how that happens. I'm going to skip the details, but that's not allowed. It'll be caught at compile time. And it's quite involved. It's quite involved in that this language lets you have objects that live on the stack. Not all of the objects have to come on the heap. Because you might have some really lightweight objects, you want them on the stack. You don't want to be dynamically allocating them and release them. You want them on the stack. So there is some non-trivial design aspects in the language about if my objects can live on the stack, and how do I prevent long-lived pointers to data within them? Well, the data within pointers are always, within objects, are always non-plain data. And kind of by construction and by some rules, you cannot keep pointers to them. You could have an object with an integer within it, and you're calling print on that integer, which is a member function of int, and in a way the pointer to the integer is the this pointer. So you're briefly constructing a this pointer, you're calling it and returning. That this pointer cannot be kept, cannot be stored in global memory. So anyhow, there's quite a few details about how this works and how it's designed, how the compiler does the work. Now this is the same bad example there. And it's kind of explaining the bad example. You have the same bad example with a string char. So again, here's the bad guy with a buffer returning a pointer that string char gave him. And it's really a pointer within buff. So this guy is a bad guy. All of these things need to be caught by the compiler. By the COOGL compiler, yeah. Yeah, not by the C compiler. The one, no C compiler catches that. No C++ compiler catches that. So just like global memory cannot point to stack memory, data on your stack cannot point to data on any other stack, whether your stack is because you're a thread or an interrupt handler, an exception handler. So there's no pointers between stacks, and there's no pointers from global memory onto stacks. Well, the compiler generates code to ensure that when your runtime stack is growing, it's checked. So it's not like you can declare an array of a megabyte and then the stack pointer gets moved out there and you're somehow smashing something that was in the heap or some other area. So if you declare something very big, all of the pages in between are going to be touched, and exceptions will be raised, etc. So basically the stack growth is checked. So let's talk a little bit about the cast and how can we give the freedom of C to a language that is meant to be safe. So I already said that a cast will let you cast as long as you're going from a pointer to some plain data to a pointer to some other plain data that is the same size or smaller. Now, if you're going from something that is smaller to something that is bigger, you would use this try cast. So you're saying, well, I have an address. I want it to be cast to a pointer to that type. I want the type of this whole try cast to be pointer to type. Now, this try cast will succeed if this address, this pointer, considered as if it was pointing to an object of the size of this guy, fits within this array descriptor. So this is an array descriptor argument here. So if it doesn't straddle past the end of the array descriptor, then it's a valid cast. If it straddles past the end of the array descriptor, the underlying memory of this plain data that this guy refers to, then instead of returning you this value casted to that type, it's going to return this other value that you put here. Usually here you would put nil. So you will get a nil pointer to that type. Now nil is a pointer that is like null. It's different, that whenever you dereference it, you always get an exception. It's not like the compiler says, oh, you're dereferencing a null pointer, I'll delete that code, like in undefined behavior in C. So that's a try-cast. Now, well, it's a pointer that is defined in the address space, and the C doesn't know that it's funny, and C has to generate the code to access it, and the compiler has to generate the right code so that C doesn't do wrong optimizations on it. So here we have some examples. So some of the casts and some of the try-casts. So for example, this first one would give a compile time error. I have a pointer to a short. I'm trying to cast a pointer to a short or a pointer to an integer. Well, this gives a compile time error. You get that error compile time. Here we're trying to do the same thing, but we're actually having an array of shorts. So we're trying to cast this pointer to a short that is pointed to the first element in the array to a pointer to an integer. We don't care if it's unaligned. If you get an alignment exception, you're trapped, but it's pointing to valid memory. So in this scenario, this will actually return this integer pointer with a proper value. We can assert that it is not nil. Now, if we're pointing at the very last short within that array, then when we try to cast that very last one, we try casting it, oh, it can't, so it's going to return you this value. So this will be nil. And then if you try to access that pointer, you'll get an exception. So say you're laying out some memory that is for some protocol, and you have some type for a header, a prefix, a body, a postfix, and a footer. And some of them are optional. This is some plain data, some networking thing you're doing, right? So you want to lay out a buffer, and some of these are going to be optional. So say you have a function that's going to make a message. And well, you pass it an array descriptor that points to the data where you're going to form the message. And you pass it a series of pointers to each one of these components. You know, the header, the prefix, the body, the postfix, etc. And so you want to do this in a C-like way. You start with a pointer at the beginning of the array descriptor that you receive as data. And then some of them are not going to be optional, so there's not going to even be checking for them being optional. But it's basically saying, try to do a cast from that pointer as if it was a pointer to a header. If there's enough space in the array descriptor, return me a valid pointer, otherwise return nil. So whatever the pointer returned, dereference it. That's a star there. And assign to it whatever this header that I received there, copy it, structure assignment. Well, that either raised an exception or not. It either fit or not, but it didn't stomp on memory beyond. Then, well, we increment by the size of the thing. Now, this one was optional. So if this second thing, this prefix, if I did get a pointer to the prefix, then I do the same thing. If it fits, assign it. If it didn't fit, you raise an exception, skip it. Again, the body is optional. Do the same thing. The posting is optional, and then you have the footer, and the footer is not optional. Now, this would seem like it's doing a lot of checks. So how would this be compiled? So if it was compiled the most efficiently as possible, it would look kind of like this. Compiler does the analysis, and it figures out that what is the size of the worst case that is being stored. So it's saying, well, the header and the footer are being always stored, and these things are optional. So for each one of the optional things, contribute to the size. And then it's going to do one test. And it's kind of a barrier like a conditional store that says, if the number of elements in the array descriptor is less than however much I'm going to store, then store a 0 into this nil pointer, which will give you an exception immediately. And furthermore, this language runtime, or this little bit of generated code, is going to actually have a compiler barrier so that the compiler doesn't start moving all of this code from here up there, because this is the stuff that would stomp on memory. But here we've checked that if this doesn't trap and cause an exception, we prevented a compiler from moving the code around this thing, then with one test, then all of the other stores can happen like they were originally written. Of course, the compiled code now is just using casts at the C level. Yeah, so all of that has to, if you're passing the array descriptors around, you're having to pass the pointer. So you're having to pass, whenever you pass a pointer, yeah, so you're always having, if you pass a pointer, the only thing you can do is, the pointer is known to refer to valid memory or be nil. So, but you cannot do ++ on it or anything unless you say, unless a compiler can see that this pointer came from that array descriptor. And if you want to move it around, it has to see, oh, he initialized a pointer with an address within the array descriptor. Oh, he's doing ++, he's doing -s on the pointer. Then he can be checking, and he'll raise an exception if you get, if you would overflow the array descriptor. So now this doesn't produce the exception and with the most fidelity. It's actually trying to store a 0 at nil. It's not actually the exact store you were trying to do. But this raises the exception appropriately. If you want it for debugging, it could maybe invoke some other generated code that actually does the store that reflects exactly the bad store you would have done even with the wrong data. So the compiler could produce additional code to have even more fidelity for the scenario that you're trying to see exactly the wrong store. Now, any object-oriented language that has base classes and inherited classes. So here we have a base and a derived class. And well, the derived class inherits from the base, and it has an extra member. So inheritance is expressed with a keyword. By the way, I didn't mention much about the object-oriented parts of the language, but basically you have constructor, destructor, copy constructor, and you have control at assignment. That's all the control you have. You don't have operator overloading, but and you also have a default constructor, all of which are optional. But so you can have value-like objects, and copy constructors are important when you're initializing an object from another, when you're returning an object by value, where you're passing it by value into functions as arguments into a function. But anyhow, you only can inherit, you have one inheritance chain that contributes data, and that's inheriting from another class. You can also implement 0 or more interfaces. You can implement as many interfaces as you want, and that makes the object model very simple. That's kind of what Java did. So the object model is simple. There's no multiple inheritance of things that contribute data. You can inherit from one class chain and 0 or more interfaces. So anyhow, here you're expressing inheritance by literally saying, well, I'm going to publicly inherit from that base class, which had a public member, and here I have another public member. And this is I have a derived class, and I have a pointer to the base. I can always assign it the address of the derived class, because a pointer to the base is always a valid pointer to the derived class. That's kind of object-oriented bread and butter. So object slicing does not occur in the language. Yeah. How do I address it? You cannot. Yeah. So you cannot pass by value. So well, so there's some intricacies here. We're going to get to it, or we might not. We're going to have to do it offline. But your object slicing, which is a thing that happens in C++ when you pass a value by object, where you just get half of the object, not the extra fields. It's one of the cans of worms of C++. So the object slicing is not allowed, and there's a whole intricate thing to prevent that. So anyhow, if you had a whole inheritance chain of things, you can do all kinds of assignments between interfaces that don't require don't require any casts. Now, sometimes you need to do an upcast. So an upcast is a cast that says, I have a pointer and I have a type, and I'm saying if this pointer to a base is actually in reality at runtime a pointer to the derived class, then the cast gives you a proper pointer to that. And if it is not, whatever value you put here, usually you put nil, you put a dummy object, whatever you want here, then it will return that value. It's just like the try cast. So whatever you want for the wrong answer, you specify here. So you have an upcast as well. So here, this code is doing a bunch of upcasts. It received an NFS file, and at some point it tries to upcast it to an NFS directory, and that fails. So you get a nil here. All of those were okay if you follow the stuff in the book. Now again, I'm not trying to only build a safe language to re-engineer unsafe operating systems written in C. I'm trying to satisfy the needs of systems programmers who are used to doing things. And quite often, systems programmers will decide to put some numeric values in pointers because it happens to be convenient to them, and they just want to put some set of numeric values in there. So the language defines a range of numeric values for which, if you ever access them as a pointer, you will get a trapping error. So these are called trapping addresses. And on a 64-bit machine, you have 4 gigs of trapping values. You have 32 bits worth of trapping values. You can assign these reliably to any pointer, which is upointer cast. And you're guaranteed that if you access a pointer that you've assigned one of these numbers that's a trapping address, it's going to raise an exception. So for whatever pointer chicanery that you need to store some numbers in them, there's a defined set of numbers that you can store, a range of numbers that will always give an exception. And the addresses are much bigger, the ones that will give you an exception. So even if your object is very big and has an array and other stuff, so it really straddles the range, it will always give an exception. The nil pointer by itself is a trapping address. Null is unsafe for a bunch of reasons. A, because the address space of the operating system, say in user mode, is defined by the operating system, and near a null pointer, there might be memory that's addressable. Some machines, like AIX, for example, has readable stuff at 0. They have zeros at 0 and some other stuff you can read around 0. So if you dereference a null pointer, you might not get a trap. You might get some junk data or some other null, depending what you touch. So use of null also is problematic because the C compiler itself, any use of null, it will try to optimize based on undefined behavior. So the language needed to define its own version of null pointer. It's called nil, and it has a different bit pattern. And the most ideal machine, null and nil, would be the same value, and you would have that part of the address space reserved. But that's not going to happen overnight. So anyhow, there's a whole scheme that says pointers to user-defined objects can never have the values 0 or null. Pointers to user-defined objects of class type can only have the value of a valid pointer or a trapping address that you chose from these trapping ranges, or nil. So by construction, all of the pointers in the object-oriented side are safe on that side. You still need to have null because you're bridging into code that you're re-engineering your kernel, and that all of that code is passing nulls around to mean not passing a thing. So for a while, you have to have null. But the end of the story is if you have a body of COOGL code and you're still using null, it'll be an unsafe program. Unless by construction, you're writing the kernel and you've decided, you've laid out your address space right. But the underlying C compiler might be doing its own undefined behavior stupidity. So to even use the null pointer, you have to pass an argument to the compiler called -- null, and that opens this kind of compatibility bridge. Excuse me? Yeah, I know. So Okay, so there's a whole discussion about how null has to go and why does it have to go, and okay, so let's ignore all of that discussion of that. Okay, so of course, junk values in memory. So if I have some data that is plain data, it's a buffer, and the buffer is on the stack, and I'm going to read into it, it's going to have junk values because I don't want to pre-initialize my buffer on the stack that I'm going to call the read system call and bring some data into it. I don't want to have to put zeros on it just so I'm going to read my file data into it. That's kind of silly. So any plain data can be uninitialized on the stack. It's not going to lead to unsafety if you're using it as a target of a system call or other things. On the other side, if you have some plain data that's got an uninitialized value and you use it as an index, or if you use it as something else, the underlying C compiler might say, oh, he's accessing memory that's not initialized. And then the undefined behavior C compiler writer guys, they invented a term, wobbly data. You read that variable, you get a value. You read the same variable later, you get a different value because it was uninitialized. The compiler is giving you random values, though you actually would have deterministic values in the real machine. But they define wobbly data and then they do whatever they want. So all of the cases where you're using even plain data that the compiler is seeing that you're using it that is undefined, it's going to give you a compile error. Now, if you have a buffer, an array of characters, and you're calling into a system call that is supposed to set those things, it's not going to give you a compile error there because at that point, the underlying C compiler doesn't know that the read system call didn't read every bit, so they cannot do their wobbly data optimization and create confusion. So, there's this idea of having deconstructed values that says that when an object first comes into being, say because it came from the heap, before you actually constructed the values, if you could actually see them, all of the values would be 0, and all of the pointers would be nil, and all of the array descriptors would have their start and end pointers as nil, and all of their max number of dimensions as 0. So the reality is that the compiler is not going to let you access things before you construct them. Now, the counter of that is if I have a pointer to an object and I have deconstructed the object, it has to take some values that are well defined. So at deconstruction time, after everything is deconstructed, the compiler and the memory manager, the releasing code are going to ensure that all of the values have zeros, but all of the pointer-like things, pointers and array descriptors, have nil in them. So that makes the memory that has been freed have well-defined behavior. Now, this is approaching, and we probably can maybe use 10 more minutes. So you have a language that is not garbage collected. How do you deal with, you have memory you allocated, now you're going to free it, and then it's going to get reallocated for a different purpose. You have old pointers and new pointers. Do you solve that problem? How do you solve that problem? It's kind of the problem of garbage collection. What do you do in that case? So the allocator for dynamically allocated memory, which is implemented in the language, brands the memory. So once you have used a page of memory, say 4K of memory, for a specific purpose, all of the objects in that page will be of the type. They will all be of the same type, and the objects can straddle the page boundaries. But all of the objects will be all of them will be of the same type. And furthermore, when you free objects within that page, and in the future you need more memory, you can only allocate objects of that type from that memory. So the memory gets branded. We're in the world of large machines with 64-bit address spaces. Even the phones have 64 bits. Yeah, they're still 32-bit, but even 32-bit on a really tiny machine has a lot of address space. So the allocator, this one implementation, this way of doing safety, brands the memory. So the data is laid out dynamically onto pages, and as soon as you designate these pages for this kind of objects, it will never hold objects of a different kind. So even if you had a pointer that was hanging out there, pointing to an object that got destroyed, it will only see either the values that were constructed, or as it was being deconstructed, they were all becoming zeros and nils. So you're looking with a pointer at a carcass of an object that cannot lead you to unsafety, in the sense that any of those pointers cannot become pointers of a different type. Excuse me? Well, so the alignment is it's its own discussion, but this doesn't force weird alignments, or there's no issues with objects straddling page boundaries and whatnot. Now, the reality is most object-oriented systems, most pieces of software out there, they might have a lot of types, but most of the types, they have a few objects of the various kinds. And then for a few of the kinds, you have many, many objects. So what tends to happen in the allocator is that you have, a few objects, small number of objects of a bunch of types, and then you have some objects for which you have an explosion of objects that get created, then maybe they get deleted. And then in the later phase, you create a bunch of objects of a different type, and you cannot use those same addresses. And you create a bunch of objects of a different type, and you cannot reuse the addresses. So if you really released all of the objects, or a lot of the objects on the first objects that exploded first, you deleted a lot of them such that a lot of the pages are now empty. You can take the memory manager, if you're the kernel, you are the memory manager. You can take that page, unplug it from the address space, or you can advise the kernel, I won't need this thing if you're in user mode. And then you can give that page back to the memory manager. And when you need in memory on the other side, it'll reuse the physical page, but not with the old data. So you're basically branding the addresses tied to the types. There are system calls, for example, in Linux in user mode that let you do these things such that even when you've given away the pages that used to contain objects, if you touch them again, you would get a zero-filled memory, let's say. Well, zero-filled memory would have nulls where the pointers are. It wouldn't have nils, which would lead to the unsafety related to that. And for example, in Linux and other OSs, you have other things. In Linux, you have a user fault FD mechanism where you can say, for this area of memory, when a fault happens, don't just give him a zero-filled memory. Call this exception handler, like a SIG bus, in the context of the guy that faulted, and it can craft a page with all of the nils in the right place. And then it gives it to the kernel, and when the page gets materialized, it has all of the nils in the right place. So there's not a window where suddenly you ended up with a page of zeros where you needed a page of zeros with nils in specific spots. Of course, if you're the kernel itself, you can do all of this on your own behalf. Yeah. Yeah. No, you can actually, so if you use this user fault FD, so say you memory map from dev0 some memory, and this mem map from dev0 or from user, from some anonymous memory source, this is going to be your heap. And as you touch the memory, you get these zero-filled things, but nobody has pointers to it initially. So the allocator can just touch them and form them. But once you have a page that you decided that there's memory pressure, all this page doesn't have any objects allocated, they've all been freed, then you can tell with some other system call that says, I don't need this page, reuse it for whatever, put it in the free list, whatever you want. But if you have set up this user fault FD range for that same thing, when you touch that thing, the thread that touches it, it could be the allocator, or it could be some buggy code that has a pointer to it from the past. Well, you want the page to be materialized as an uninitialized object. Now, that's one half of how to do safety. The other half of how to do safety is that pointers themselves are value objects. You can actually define the constructor, the destructor, the copy constructor, and the default constructor for pointers. So you can turn a raw pointer into a smart pointer, and you have life cycle. You have control of the life cycle of what you have made your smart pointers be. So in your own ways of doing other ways of doing safety, you can do the equivalent of smart pointers, reference counting, or anything else you want. If you might need garbage collection for some types. So this notion of doing smart pointers lets you do that for specific types. Or if you wanted to implement garbage collection for everything, you could do it too in the language. But when you're trying to define a language, so basically the goal is, if I can prevent pointers to be mutated and forged to point to pointers of other types, such that they defeat the type system, then I cannot make this safe. If I can prevent pointers from being forged by one means or another, then I have a much closer assurance that this is safe. Now, there might be arguments that say, well, you have destroyed this object. It's now become a carcass. It's got these zeros and these nils. Now you have a confused program with pointers to this dead object. They're still touching this dead object. Maybe they will trap soon enough when they touch the nil. Or maybe they will run confused for a little bit. But will they do actions that lead to smashing the stack, or to smashing some other random data, or smash in a function pointer that I go execute random code? No. So the idea is to prevent those things. You're going to prevent those things.
So that's why we're playing data type is as extensive as it is. Because all those things might cause wrong behavior, but they won't cause stack smashing.
Yeah. So you're basically again, we're trying to be in the real world where you have this amazing body of C code and you cannot do anything to this amazing body of C code. You got to preserve it. How do you make that safe? Well, this is as close as you can do feasible incrementally. And yeah, you can begin to re-engineer these systems to do smart pointers and to do other things so that you don't have long-lived pointers to carcasses. Yeah, exactly. Yeah. Now, by trying to keep the indexes as safe data, the things that you're going to index so that you don't like kind of have created an alias into index and smashing those, that would be good too. Now, a lot of the indexing into arrays are done with local variables within a function, and you can declare it int or any other type you want, size t, whatever. Well, that's going to be safe because you cannot alias concurrently this memory. The only one that can have a pointer to that data is your own self, or some function that called you in your same call chain, so it's not concurrently being changed. So nobody's changing things under the back of the compiler and local variables, because you cannot give addresses of local variables to other threads. Anyhow, I wish we had more time. There's a lot of details, but there's a Kickstarter. I was trying to, well, all of this work has been the work of myself so far. Somebody has helped edit the book. But I was trying to hire a compiler writer to finish this work because I just come out of a startup for 2.5 years, which wasn't related to this. And I'm now at Google working on stuff. So if I can get them to fund or contribute, there's all kinds of asks for money. I'm trying to get corporate money, nonprofit money, individual money, and there's all kinds of, books that will be written, autographed, and whatnot. So if you guys think this is a good thing to support, I would love any feedback about the language. There's probably some fundamental flaws that anybody that can find the flaws, or whether it's a nit or anything, I would love to hear any feedback on the language. If you want to contribute, that would be great. If you don't want to contribute, spread the word. If you think that this is worth the while of the engineering community to get us out of this pickle of all of this unsafe code that we've created for the last 30 years. I heard a quote in the Computer History Museum. Ken Thompson, the father of Unix, the father of C, right? Of chess machines, the Go language. Ken Thompson did Golang with Pike at Google. And he did a bunch of other stuff, chess endgames and whatnot. He himself was in the Computer History Museum, and he told one of the historians that if he knew what would have happened with all of this unsafe stuff, he would have never allowed the release of Unix and C out into the wild. Just look at the disaster we have now. So anyhow, Go, the language that he created recently, the last 5 years or whatever, is safe, doesn't have undefined behavior, is garbage collected, but it's different enough from C that you cannot, with a straight face, say, I'm going to rewrite the Golang, but it's called the Go programming language, right? Just the website is golang.org, whatever. But you cannot, with a straight face, say, I'm going to rewrite Linux into Golang, because it's just too far. There's no way to do common code or incremental. So anyhow, I I appreciate that you come, and any support, spread the word. I appreciate that. I have done no publicity to the Kickstarter because I started it, and then like the next week I started at Google. So it's just sitting there. So it probably has like 3 or 4 weeks to go. Somebody put like $60. Zero publicity. But with these talks, maybe I'll get some publicity. I'll give some talks at Google, and maybe I'll try to do like a talk at CPPCon. And there's a lot of Googlers that are worried about this problem, worried about the problem of undefined behavior. And there's a lot of people in the industry that think we have to do something to advance this sorry state of affairs we're in. Anyhow, thank you very much.